Welcome back, folks. More superposition. It scales. It just doesn't scale real nice. So we can handle problems with more supplies. And you're going to have to do that in future classes, but we're going to start to do that with programming more, which is going to be better all around. Anytime you have to do a task repeatedly, get a computer to do it if you can. Okay, so here it is. Count the number of independent supplies, and that's going to tell us how many subproblems we need to break it into. So let's see here. I'm going to do my cut and paste trick here. We've got one. That's an independent supply. So is this one, right? It's not dependent on any other value. That's the other form of independent voltage supply. So I wanted to get them both in the same problem so that you can see that we treat them both the same as far as circuit analysis is concerned. And then we've got the third one down here. That's independent. It's got the circle around it. That's an independent current supply. Okay, so we're going to have three subproblems. It just means that much more analysis. But we can do it. Let's have at it. So that's the original problem. Maybe I should scroll back up and use all of this empty space up here for something. And at the end here, we'll see. Let's get subproblem number 1. It doesn't matter the order you go in. Okay, sometimes I like to start with subproblem number 0. Depends on how I'm working the problem. Okay, I'm going to start with this voltage supply just for lack of any other. It's on the lower left. All right, doesn't matter the order you do these in. The addition at the end is commutative. You're in good shape. We replace the other independent supplies with their ideal resistances. So I take those out. That one's a voltage supply, so it's going to get replaced with a short. This one's a current supply, so it gets left open. Okay, and then we go analyze it. And we analyze it to find the first part of I out right there. Okay, so analyze it any way you want. I think it's going to be 1.5 milliamps. Let's see if I'm right. I've been doing this way too long that I can look at this problem and do that. But we have two meshes. Now this mesh ends up being weird and kind of a dog leg if you're a golfer, a kidney if you've studied biology. It's not a box. Okay, it takes a right turn, but it is a single mesh because there's nothing, there's no intermediate branches, right? Because that current supply disappears, and that's one of the funny things that can happen when you take a perfectly good circuit and you start ripping parts out of it. Okay, so it's going to be a 2x2. Let's just do some quick mesh on this. What does I1 touch? It touches 8K. Okay, what does I1 touch and share with I2? Well, it also shares the 8K. All right. And on the right-hand side, it looks like we go up 12 volts. Okay. Playing the same game for the KVL around I2. What does I2 share with I1? It looks like it shares the 8K, the same 8K, these two 4Ks together. And then what does I2 touch by itself? And it looks like it touches all 4 of these 4Ks for a total of 16K. No voltage supplies on that mesh. Okay, go ahead and solve it any way you like, as long as it's correct. Sorry about that. Negative 8K, 16K, and 0. Okay, and from that we get 3 milliamps for I1 and 1.5 milliamps for I2. What did I say it was going to be in the first? I think I said 1.5 milliamps. But that's I2. That's not the first part of I out. Okay, does I1 touch I out? Sure does. And it goes in the positive direction. Does I2? Well, we got to kind of trace our way around this way. And it does touch it. And it goes in the opposite direction. So it's going to be minus I2. Plugging in values, we got 3 milliamps minus 1.5 milliamps So it does end up being first part of I1, or first part of I out, it does end up being 1.5 milliamps. Okay. Whew. First subproblem done. That was kind of behind my head. I think you can still see it there. Don't reuse any part of the analysis. We're building a different circuit now. Okay, but let's get on to subproblem number 2. Come on. There we go. So same circuit. We got to pick a different source. I don't know what you would pick if you were here with me. It doesn't matter what we pick, as long as it's not the same one that we just did, right? So we know we're getting rid of that one. Let's do the other voltage supply. Okay, that was a voltage supply, so it gets replaced with that. Let's see what this one does. Okay, in order to see what that does, we get rid of the current supply and leave it as an open. That's its ideal resistance. Again, I'm going to cover that why that's the ideal resistance when we look at the next 2 theorems. Okay, setting up to do some analysis. This is not the first part. This is in fact the second part. There we go. I1. I2. All right. 2 by 2 once again. What is I1? And 2 kVLs. There's no current supplies yet. What does I1 touch? It touches a total of 8K. What does it share with I2? It shares a total of 8K. Inverting this. There are no voltage supplies. Okay. What does I2 share with I1? Well, it's that same 8K. And then what does I2 touch by itself? It looks like it still touches a total of 16K. Going around clockwise, we're going from negative to positive, so that's going to be a positive 12 right there. Okay. So let's figure out what that is. Okay, 8K, negative 8K, 0, negative 8K, 16K, and 12. And we get 1.5. Oh, I didn't predict this one. I probably could have. Yeah, this one's 0. So we get both mesh currents are 1.5 mils. Putting it together so that we have the second part of I out. Let's see, does I1 touch that? Yes, it does. Does I2 touch it? Yep, and it flows opposite, so it looks like that. So plugging in values, we get 1.5 milliamps minus 1.5 milliamps, also known as 0. Okay. Like, this is shorted, right? Together, these two are in series, and they're connected together, so there's no voltage drop across these two resistors. There's no voltage drop, no current's going to flow. So that kind of passes my gut check, just looking at the circuit. Okay. Last subproblem. Okay, rinse and repeat and repeat and repeat. Why wouldn't you just use mesh or nodal? Because sometimes you can't. Okay, when you have multiple frequencies in the circuit, you can't. We're not going to cover it this semester, but it's a very important stepping stone to do some more sophisticated analysis. Okay, last one. What does this current supply do to I out? Well, we got to replace the other independent supplies. They're both voltage supplies. So they're both going to be shorts. Look how popular I am. And sloppy I am for not turning off my phone. Okay, set up to do some mesh analysis. Can you imagine if you had to do this all the long way? There's a reason I taught you the shortcut. There's a reason I taught you the shortcut. Okay, let's try to buy as much real estate as we can here. What does I1 touch? Oh, no. We got a super node. Nice, right? Or, no, not a super node. Super mesh. You thought you could brain dump all that stuff. Here's your super mesh. We're going to go all the way around here. Okay, I looked at it. I almost wrote all KVLs. There's a current supply. I got to write one KCL. So let's write that KCL. Does I1 touch the current supply? No. Does I2 touch the current supply? Yes. And it goes in the same direction. Does I3 touch the current supply? Yes, but it goes in the opposite direction. So that's -1. Invert that. And we've got 6 milliamps on that side. And we are finding the third part of I out. This one's going to be 3 mils. You believe me? I believe me. Okay. So that's the KCL for the super mesh, super loop. Let's write the KVL for the super loop. So what does I1 share with the super loop? It shares both of these 4Ks. So we're going to get -8K. What does I2 touch that's on the super loop? It touches these two 4Ks. So that's going to be 8K. And then what does I3 touch that's on the super loop? It touches these two 4Ks for, again, 8K, but it's a different 8K. And I don't see any voltage supplies, so that's going to be 0. Okay. Last one is the KVL around I1. What does I1 touch? It touches a total of 8K. What does it share with I2? -4K. What does it share with I3? -4K. I'm hoping by repeating these questions over and over, they are coming out of my head and into your head. I can hope, right? As a teacher, I can hope, maybe. Okay, 0, 1, -1, 6 mils, -8K, 8K, 8K, 0, 8K, -4K, -4K, and 0. That's 0 amps, 3 milliamps, and -3 milliamps. Okay, from that, we come back and we look at the third part of I out. Does I1 touch it? Yep, and it goes in the positive direction. Does I2 touch it? No. Does I3 touch it? Yep, but it goes in the negative direction. So it's going to be I1 minus I3. Plugging in values, we've got 0 minus -3 milliamps. And that ends up being +3 milliamps, just like I predicted. Okay. Oh, let's see. I looked at these two resistors. How did I get that without doing any analysis? I looked at these two resistors and I said they are in parallel. They share the same two nodes, right? Because now this wraps all the way around. And I know that I have 6 mils flowing out of them. Looking at their resistances, they are equal. So I knew that this 6 mils was going to divide evenly between those two resistors. Okay, so we've got our 3 parts here. Let's do this up above, make the images a little smaller, right? Let's scroll back up here and collect our hard work. Wouldn't it be great if we could get a computer to do this for us? Okay, there's I3. The third part of I out. Here's the second part of I out. And come on. Oh, I moved that. Oh, that's horrible. Oh, the humanity. All right, let's go grab it again. Oh, it's 0. How uninteresting is that? Okay. What that's telling me is that supply, whatever supply I was analyzing there, which one? That 12 volt supply doesn't contribute anything to I out. You can make it whatever you want. It's not going to add any current. And that's just because of the way everything's connected. Okay, so in order to do this, summation at the end, we say I out is the sum of all three. .5 milliamps plus 0 plus 3 milliamps is 4.5 milliamps. All right. That is superposition. It does scale. We can do it with more supplies. But that's the answer we're after. It's not a great way to do circuit analysis, but we have to do it. We have to do it because we're going to build from it in future classes. Okay. I think from here we move on and we figure out what to do with dependent supplies in superposition. I promised you I'd do that, and I'm going to do it. So stay tuned and good luck.